In this section, we're going to look at reinforcing steel. Several slides from this presentation are from the Concrete Reinforcing Steel Institute, or CRSI, essential presentation. By the end of this section, you should be able to explain the design and construction process and where reinforcing steel fits in, identify the most commonly used types of steel, identify the associated yield strength of different grades of steel, use the standard reinforcing bar size chart to determine the nominal diameters and areas, draw the standard stress strain curve for reinforcing steel, grade 60, and label the important points, use different model idealizations to relate stress to strain and also strain to stress, explain how reinforcing steel responds under low cycle fatigue and calculate the number of cycles it takes to fail a reinforcing bar, describe how steel is affected by strain rate and quantify this effect using dynamic increase factors, explain strain aging of steel, and finally, describe some considerations that go into a reinforcing cage and list strategies for reducing congestion. As a design engineer, you will specify the number of bars, spacing of bars, size of bars, strength of bars, type of steel, and location of bars. The contract will then take your drawings and create shop drawings with specific details on the reinforcement, bar lengths, bar diameters, type of steel, and how the actual rebar cage will be constructed. These shop drawings will then be used to create rebar schedules, which show the specific details on the reinforcement and the number of each piece that is needed. The reinforcing steel fabricator then gets steel from the steel mill and produces all the bars with proper lengths, sizes, and bends required for the project. These bars are then delivered to the construction site and the building is constructed. Reinforcing steel is produced per ASTM standards for chemical and physical performance. There are several different types of reinforcing steel that we'll discuss in this section. In general, reinforcing steel used in reinforced concrete construction is made from at least 97% of ferrous scrap material. These are recycled steel materials. So reinforcing steel is a recycled product primarily. Reinforcing steel is produced initially at steel mills and fabrication shops. There are steel mills and fabrication shops that are located all over the US, so there should always be a steel mill and a fabrication shop located close to your project. There are several different types of reinforcement, which we're going to step through on the next slides. Each type of reinforcement has a specific application, which I'll also highlight. ASTM A615 carbon steel is the most common and basic of all the reinforcing steels. ASTM A615 grade 60 bars are the most widely used and inventoried reinforcing bars. So this is likely the reinforcement type that you'll use for your project. Note that A615 reinforcing steel does not have good weldability, so welding it can lead to brittle connections. Low alloy steel deformed bars conforming to the ASTM 706 standard are intended for applications where controlled tensile properties, restrictions on chemical composition to enhance weldability, or both, are required. Deformed non-prestressed longitudinal reinforcement resisting earthquake-induced moment, axial force, or both in special moment frames, special structural walls, and all components of special structural walls, including coupling beams and wall piers, must be ASTM A706 grade 60 steel in accordance with ACI 318. ASTM A767 reinforcing steel is coated with a zinc layer that provides corrosion protection. It is applicable exclusively to hot dip galvanizing of reinforcing steel, which involves completely cleaning the steel and then immersing it in molten zinc. The molten zinc reacts with the steel surface to form stratified zinc-iron alloy layers, which are metallurgically bonded to the steel. These types of reinforcing bars are usually used where corrosion may be an issue, such as in bridges or tanks containing liquids. ASTM A775 reinforcing steel has an epoxy coating that protects the bar from corrosion. The coating, which is typically green, is applied before fabrication. Similar to ASTM A767 reinforcing bars, epoxy-coated bars are used in environments where corrosion may be an issue. Note that chips in the epoxy can lead to concentrated corrosion though, so care needs to be taken when handling epoxy-coated bars. Similar to ASTM A775 reinforcing steel, ASTM A934 reinforcing steel is also epoxy coated. Coatings for ASTM A934, which are applied after fabrication, are typically purple or gray. ASTM A955 reinforcing bars are made of stainless steel, which provides resistance to corrosion. Certain alloys can be manufactured to be used in applications where controlled magnetic permeability is required, such as in slabs or walls surrounding medical equipment that is sensitive to magnetic items. This steel is also used to control corrosion. ASTM A996 reinforcing steel is produced by heating and re-rolling train axles or steel rails into deformed reinforcing bars. Bars made of axle steel are designated with an A, and those made from rail steel are designated with an R. ASTM A1035 reinforcing bars are high-strength reinforcing bars with yield strengths of 100 KSI and 120 KSI, which are designated grade 100 and grade 120 respectively. These reinforcing bars are commonly used in applications where the high yield strengths can help reduce congestion. Further applications using these bars is currently being researched. ASTM A105 reinforcing bars have two coats of protection for corrosion, a zinc layer underneath an epoxy coating. The reinforcing steel grade is a value assigned to specify the yield strength for which the reinforcing steel was manufactured. As noted previously, the most commonly used reinforcing bar grade is grade 60, which has a yield strength of 60 KSI. This is also the most commonly available material. Different types of reinforcing steel can also have special chemical restrictions and/or special requirements. Here are chemical restrictions and special requirements for ASTM A615, A706 low carbon steel, and A996 steels. Shown here are the standard ASTM reinforcing bar sizes found in the US. Bar sizes 3 through 8 follow the rule of 8s. So you can take the bar number divided by 8 to determine the diameter. A number 3 bar will have a diameter of 3/8 inch. A number 5 bar will have a diameter of 5/8 inch. You can see here also each reinforcing bar has a standard nominal area. This area is not equal to pi r squared for the bar, so use the nominal bar area in your design. Standard reinforcing bars will have deformations on the sides of them. These deformations are the ridges or ribs that encircle or wind around the bar, and they should be considered when determining the available space between bars. These ridges interlock with the surrounding concrete to help create a strong bond between the steel and the concrete. ASTM specifications require that identification marks be rolled onto the surface of a reinforcing bar, as shown in this slide. The marks facilitate bar identification in the field. The first identification mark, which is usually a letter, identifies the mill that produced the reinforcing bars. Mill identification marks for U.S. manufacturers are given in the Appendix A of CRSI's Manual of Standard Practice. The second identification mark is the bar size. The third mark identifies the type of steel that was used in the production of the reinforcing bar. A summary of the ASTM designations and identification marks is as follows. ASTM A615 has a mark S. ASTM 706 has a mark W. ASTM A996 rail has a mark of I or R. And ASTM A996 axle has a mark of A. Bars marked with an S and W meet the specifications for both A615 and A706. The fourth identification mark is the minimum yield strength, or grade designation, which is required for grade 60 and 75 bars only. Grade 40 and 50 bars are required to have only the first three identification marks. In lieu of the grade number, a grade line can be used. For grade 60 bars, one additional longitudinal rib, or grade line, is rolled onto the bar, as illustrated in the figure on the left. Two additional longitudinal ribs are required for grade 75 bars. We'll now look at the stress-strain behavior for steel. Shown here is the typical stress-strain behavior for a grade 40 or grade 60 reinforcing bar. You can see that we have linear elastic behavior up until our yield point. When we yield, we'll have some length of a yield plateau until we move into the strain hardening region. We'll continue to gain strength in the strain hardening region until we reach our ultimate strength, and then we'll fail the reinforcing bar. You can see some typical values for a grade 60 reinforcing bar. Our yield strength is going to be around 0.0021 or 0.0206 strain. Our strain hardening region is going to start at around 0.01, and our ultimate strain will be around 0.1 strain. If we zoom into the point around our yield point, we can highlight several additional characteristics of our stress-strain curve. First, we can see that our slope for our steel is always around 29,000 KSI. We'll have an upper yield point that'll be above the initial yield point. So as we're loading our bar or our steel, we'll go above our yield point for a little bit and then drop back down. Typically, we'll ignore this upper yield point when accounting for the stress-strain behavior of steel. You can then see our initial slope of our strain hardening region is between 1/10 and 1/20 the stiffness of our steel. Here we can see how our reinforcing bars will actually fail. You can see that our reinforcing bar is going to fail because of necking in the reinforcement. So what happens is we'll have a localized strain concentration that'll lead to failure and fracture of the bar at this location. So the stress-strain response of our steel will depend on what strains we're monitoring. If we're measuring strains between points or between the 2 points here shown by 1, we'll see a drop-off in strain as we approach failure. If we're measuring the average strain, which encapsulates our failure, then we'll see this response here shown by 2, with still an increase in strain and as we drop in stress. And if we are capturing between points or between the 2 points shown in 3, we'll see more strain than we do in the other points. The grade of the reinforcement or strength of the reinforcement is going to impact our stress-strain behavior. The higher the strength, the less ductility, and we'll have less of a pronounced yield plateau or yield point. So in grade 60 reinforcing steel, we'll still have a bit of a yield plateau. But as we get to grade 75 and especially in grade 90, we won't have as much of a defined yield point. If we don't have a defined yield point or yield plateau as we do with grade 60 steel, we need to use the 0.2% offset rule to determine the yield strength. The 0.2% offset rule takes a line with slope ES shifted over 0.2% or 0.002 strain and then looks for the point where that line intersects our curve. Your yield strength is then that point where our 0.002 offsetted line intersects with our curve. And we'll use this rule for steel with 75 KSI yield strengths and higher. Note that there are currently yield strength limitations that are specified in ACI 318. So we have limitations for the maximum values of Fy for different applications, for our flexural members, for shear reinforcement and lateral support. As we continue to get more research with higher strength steels, these limits will continue to increase. Shown here are several different ways that we can idealize the stress-strain behavior of our reinforcing steel. The first is elastic perfectly plastic. In this model idealization, we assume that we have elastic behavior up until yield, and then we stay on our yield plateau or remain with our Fy until we reach failure. This may not be applicable for situations where we need to understand the true ultimate capacity of the section, such as in a capacity design. Next, we have a trilinear curve where we assume that we have elastic behavior up until our yield plateau, and then we assume that the initial stiffness of our section is like around 1/10 of ES, so the initial stiffness of our strain hardening region. So this is applicable for sections where we're just a little bit over our strain hardening strain. Finally, we can also consider the complete curve, where we use a linear relationship up until yield. We assume that we're on the yield plateau up until the start of our strain hardening region, and then we use some polynomial expression to approximate the behavior of our strain hardening and ultimate strength region. We'll next look at the stress-strain behavior under cyclic loads. Here we have our quasi-static relationship, and I'm highlighting here what's called the Balchinger effect. The Balchinger effect essentially says that when you load your reinforcing bar initially, you'll have a defined or sharp yield plateau or yield point. Every additional cycle after that will have kind of this rounding off, so we'll no longer have a defined yield point. And you can also notice here we have about the same stiffness as our initial loading as we do in all the unloading and additional loading cycles. Shown here is the typical stress-strain history for a strain-controlled test. In this figure, we see the results for a number 7 bar that was cycled between negative and positive 0.025 strain. You can notice that it takes less stress over time to cycle between these strains, and this is caused by the relaxation in the steel. We can also look at this response in terms of strain versus time. So we can see that the first cycle we would go from our epsilon max to our epsilon min. The distance between peak and peak is called a half cycle, and the distance that it takes to go from 0 strain through the max, through the min, and back to 0 is called a full cycle. So we can look at our average strain as a function of our max and our min divided by 2. So our epsilon max minus our epsilon min divided by 2 to find our average strain. We can then use the average strain to figure out the number of cycles that it'll take to fail the reinforcing bar in low cycle fatigue. So we'll do this on the following slide, but we'll use this equation here, where NF is the number of full cycles to cause failure, or 2NF is the number of half cycles required to cause failure. Capital M and lowercase m are constants that are dependent on the bar size. This relationship is linear in the log plot, so we can plot the number of cycles to cause failure based on the average total strain. And you'll see in the log space, and it'll be a linear relationship. In this slide, I give you an example problem to show you how you can calculate the number of full cycles required to cause low cycle fatigue in a reinforcing bar. So in the example, we have a number 7 bar is cycled from 0.02 to negative 0.02 strain. And the question is, how many full cycles can the bar withstand? Note from our table for our number 7 bars, our capital M is equal to 0.11 and lowercase m is equal to negative 0.44. And these, remember, are our experimentally derived constants. So we can just plug into our equation and find our average strain. 0.02 minus negative 0.02 divided by 2 will give us 0.02. And then we can plug this in and calculate the number of half cycles required to cause failure. So plugging in our average strain and our 2 constants, we can see that it'll take 48 half cycles to cause failure. And then dividing by 2 gives us the total number of full cycles required to cause failure. So cycling a number 7 bar from 0.02 to negative 0.02 strain would cause failure in 24 full cycles. The actual strain versus time plots are not always so clean, as is the case with seismic loading. So we need a way to calculate the low cycle fatigue limits or capacity under these irregular strain versus time plots. Miner's rule is a way of doing this. Essentially what we do is we figure out the number of half cycles required for failure under each of the half cycles in our strain versus time plot. Then these half cycles cause some kind of damage to our reinforcing bar. So we can sum up that damage, and when our damage equals 1, we'll have failure of the reinforcing bar. So in this plot, highlighted is a min to max strain, or this is a half cycle. So what we would do is find our 2 NF sub I, so the total number of half cycles required to failure if we were to cycle between peak and peak. Then take that total number of half cycles, or 1 divided by that, and that would be the total damage caused by this portion of our strain versus time plot. So we can do that for each of our peak to peaks to figure out what damage is caused by each one of these components of our strain versus time plot. And then when our damage equals 1, we have failure of our reinforcing bar. Next, we're going to look at the strain rate effects on steel. So the rate at which we apply a load on our steel is going to affect the response. So you can see here, the strain rate is going to impact our yield stress, our ultimate stress, and our total elongation differently. So our strain rate is going to have a dramatic effect on our yield stress. As we move from static into dynamic strain rate, you'll see that our yield stress will greatly increase. You can see that it'll also affect our ultimate stress. So as we move from static to dynamic, we'll have a smaller increase in our ultimate stress. And you can notice that as we approach very fast strain rates, our yield stress is going to approach our ultimate stress. So they'll be near equal as we get into very fast strain rates. You can notice that the strain rate in the static range, it does have an impact on elongation, but in the dynamic range, it doesn't have much of an impact on the total elongation or ductility of the reinforcement. Shown here are the stress strain curves for several different strain rates. What we can see is that a higher strain rate or faster loading is going to increase our yield strength. This has the largest impact. It'll also increase our ultimate strength, but not as much as our yield strength. And it's also going to bring our yield and ultimate strength closer together. So you can see here in the fastest strain application, our yield strain is about equal to our ultimate strain. We have a slight increase in our total elongation. So you can see this when we're in the static range. So our slowest strain rate has an ultimate strain, as I'm highlighting here. And as we increase even in the static range, we'll have a higher ultimate strain. But in the dynamic range, a higher strain rate does not impact the total elongation. So you can see these ultimate strains are very similar. We can account for our strain rate effects using the dynamic increase factor. This factor is a factor greater than 1 that relates our static yield or ultimate strength to our dynamic yield or ultimate strength. So if we have a certain strain rate, we can take the dynamic increase factor times our static rate to find what our yield strength would be under the dynamic strain that would be applied. The next phenomenon I want to talk about is called strain aging. Essentially, what strain aging is steel is going to yield at a higher stress after it has been loaded past its original yield point and then unloaded. So if we load our steel past its yield point into the strain hardening region and then unload it, when we go to reload it, it's going to have a higher yield strength than it did before. So we'll have a higher yield point in this already loaded steel than we did when we initially loaded it. And this is called strain aging. In the next couple slides, I'm going to be talking about specific aspects of the reinforcing cage. The first here, we'll talk about the development length. The development length of a reinforcing bar essentially ensures that a specified number of deformations are available for bonding between the reinforcing steel and the concrete. We need to make sure that the concrete and the steel are working together within our reinforced concrete structure. We can shorten the development length by adding hooks or end anchors, which will increase the surface area available for bonding with the concrete. And this can be used to shorten our development lengths from what we would need in just using a straight bar. Note that reinforcing steel is usually provided in 60-foot lengths due to shipping and handling limitations. Longer lengths are usually required for projects, so we'll need to splice the bars together in our actual reinforcing cage. It is common for reinforcing bars to be spliced together to achieve longer lengths. Splicing may also be necessary to install reinforcing steel assemblies supplied in separate sections. Also, if construction occurs in multiple phases or multiple floors, splicing is used to connect different sections together. Splicing may also be required to splice 2 or more bent bars together if a single bar bent into the desired shape would result in a width requiring a special transportation permit. There are 3 main types of splices: lap splices, mechanical splices, and welded splices. Lap splices consist of 2 overlapping bars that are possibly tied together. The total lap splice length is the total overlap length of the bars, so from the end of one bar to the end of the other bar. This lap splice length can be calculated using ACI 318. Lap splices are more forgiving of field adjustments, and they are the most common type of splice, and they're typically the most cost effective. So this type of splice should be specified whenever possible and practical. One drawback is that using this type of splice can cause congestion and also bar waste. So you can stagger the splice location to reduce congestion, but you may need to use another type of splice if your cage is too congested. Mechanical splices consist of 2 bars that are physically connected together using some kind of mechanical connector. These type of splices are manufactured with a strength equal to at least 125% of the yield strength of the reinforcing bars, so that yielding occurs away from the splice. These splices can be advantageous in congested areas, but they are typically more expensive than lap splices. Also, mechanical splices have tighter construction tolerances, as you need one bar to line up exactly in line with the other bar that you're splicing together. These types of splices are extremely strong, however. The last primary type of splice is a welded splice. A welded splice consists of two overlapped bars that are physically connected using welding. Some drawbacks include the need for a certified welder on site, which can be difficult to get a certified welder in the field. Also, the steel needs to be designed for welding, which means it needs to be ASTM A706 steel, which isn't typically used in our reinforced concrete structures. So generally, we try to avoid welded splices. Congestion can occur at various locations within a reinforced concrete structure, depending on the reinforcing bar size and spacing that is chosen. It is important to draw details to scale to ensure that all the reinforcing bars fit adequately within the structure while satisfying the pertinent ACI 318 requirements. The photo on this slide shows the congestion in a reinforced concrete column. Headed bars were used in hopes of alleviating some of the congestion, but we still have a lot of congestion in the column. One possible way to prevent congestion is using high-strength reinforcing bars. The use of high-strength steel typically results in smaller quantities of steel in the forms, which can help in alleviating any potential congestion. This photo illustrates the photo on the right illustrates two identical columns. One of the columns has grade 60 reinforcement in the back, and the other utilizes grade 100 reinforcement. It's clear that the column with the higher strength reinforcing steel has less congestion. Headed bars or end anchors can eliminate the need for standard hooks at the ends of bars and at the ends of members. And this can reduce the congestion at the ends of members and in joints between members. Mechanical splices can also be used to replace lap splices, which will help in eliminating congestion in joint regions. In the next few slides, we're going to look at the mill process for steel. We start with ferrous scrap metal being sorted. At the mill, different types of ferrous scrap metals are sorted depending on the type of reinforcing steel being produced. The ferrous scrap material is then melted. So the scrap is then loaded into an electric arc furnace and melted in a batch known as a heat. This is the material source or harvest location for LEED sustainability credit considerations. The molten steel is taken in the ladle for further refinement. Metallurgical additives may be mixed in to achieve the required strength and steel characteristic for the type and grade of steel being made. A sample of the steel is typically taken at this point for chemical testing. Next, the molten steel is poured into the caster. So the molten steel is poured into the continuous caster where it solidifies into strands. These strands are then cut into sections, which are called billets, and then the billets are reheated and rolled. And in most reinforcing bar manufacturing operations, the billets are reheated and transferred to the rolling mill, where the billets are reduced in size until the required dimensions are achieved. Finally, the dimensions and mill markings are rolled onto the surface of the reinforcing bar. The bars are then cooled, so the finished product emerges onto a cooling bed. A sample of steel is taken again for material and physical testing. The reinforcing bars are then cut into straight lengths and bundled. Some plants may roll the smaller reinforcing bars into coils. The smaller bars are frequently used in fabricating stirrups or ties. Finally, the bars are delivered to the fabrication shop where they will be fabricated based on the structural drawings and design specifications. Here's a list of references for further study on reinforcing bars.